Welcome to FutureDrH. Today we are going to do physical science, focusing on the physics part, and the part that we are going to do is vertical projectile motion, answering the question that was just written last year in this question paper. So without wasting any time, I'll go directly to the questions. So here are the questions here. So if you check here the scenario that we are given, it says that a ball is projected vertically upwards from the top of the building that is 5 meter high, and ignore the effects of friction. So, and then they say that the table below shows the magnitude of the velocity of the ball at 3 times during its motion. So here we are told that a person is directly here on the top of the building, and then when the person projects the ball 5 meter from a building 5 meter up, and then we are given this graph. So this graph tells us that at time zero is the beginning of the motion. So when we did not start counting time yet, that is the beginning of motion. So at the beginning of the motion, the velocity of the ball was 15 meters per second. So that's just a way of telling us that the ball was projected upwards by 15 meters per second. So here at the place of projection, we can just come and say 15 meters per second. And then another thing that we are told is that there was a point of time where the velocity was zero. And where is that point? Uh, Everywhere where the velocity is zero is called the maximum height. So this is the maximum height. We can call it point P because the ball is going to go up until point P, and then it's gonna come back down here, and then it's gonna bounce again. After it bounces, it's gonna reach a certain maximum height. So and then so this is point P. Let's read about point Q. We haven't read about point Q yet, so we'll learn more about point Q as we go. So this is the information that we're given so far, that the ball was projected by 15 meters per second upwards. So they say define free fall. Free fall is the motion in which the only force acting on an object is gravitational force. So free fall is a motion, and another definition which is similar to that one is projectile. Projectile is an object. A projectile is an object. Free fall is the motion. A projectile is an object that has been given initial velocity and goes under gravitational force only. So, and in another way, you can just say a projectile is an object that goes that's given initial velocity and undergoes free fall, because free fall is that motion in which this ball is moving after it has been projected, where there's only one force. So if they say draw the free body diagram of an object that is undergoing free fall, there will just be Fg, or gravitational force only. So, and then they say that using the equations of motion only, calculate the value of P. So, what is this P within which they need here from the graph? So the P here is the time that it takes from the when the ball was projected here from the top of the building to reach there the maximum height. So what time does it take to get there? So in order to calculate that, you must uh, choose a segment of motion. First, you must first choose, sorry, I'm dealing with the segment of motion from the time of projecting to the time of reaching the maximum height. So you are going to name each and every variable that you have according to that. So let's name each and every variable. So v initial, so it is here from at the point of projection. So what is v initial? So another thing that is very much important is to choose direction. So let's choose direction to say up is what? Up is positive. So v initial, because it's projected upwards, it's plus 15 meters per second. Or if you want, you can choose not to write it. And then when we go to v final, so a v final and v initial depends on the section of motion that you have chosen. Because you have chosen from the time of projection to the maximum height, it means that the final velocity is the velocity where the segment of motion in which you have chosen. So here it is at the maximum height. At the maximum height, velocity is always what? Is always zero. So here we are just listing the variables. We are just listing what we are given according to the information, and then after we'll just figure it out, or which formula can we use to plug and solve this. So another variable that is always given, it's gravitational force. It's always there. This one you don't need to be told about it, because it's always downwards and up is positive. Downwards will be what? Negative. So in projectile motion, we are dealing with a free fall motion where each and every object experience a gravitational force. So, what's the other information that we have been given? And we must remember, or what do they want here in the question? They want the P. What is our P? It says here in the graph that our P is the time. So we must just write our time there, so that we know that we are solving for it. So if we check the information that we have listed so far, is there a formula that we can use to find our time? So yes, there is a formula that we can use, which is V final equals to V initial plus A change in time. Or you can just scroll here to see the formula sheet. The formula that I chose is this one here. So let's go back to continue solving our question here, and then we are just gonna plug in everything with its sign. And then the initial velocity there is plus 15, and then we say plus negative 9.8. It's very much important to not miss out the signs when you copy. So, and yes, just gonna give us so we are just gonna bring 15 that side, and then divide by negative 9.8, and then it gives us 1,53. So 1,53, those are the seconds it takes to reach the maximum height. So here I'll just write 1,53 so that I can wrap and use this space here. So another way that is very much interesting is that what matters is the section of motion that you have chosen. If you draw the motion of the ball, it starts from the building, and then it goes up and comes back to the same level and goes down again. So you could have we could have also chosen this segment of the motion from the time that it comes from the maximum height, and then we are going to use this as our initial velocity of 0. And then another thing, another here, when it comes to the final velocity, we are going to choose final velocity as the same velocity that it got up with, because the velocity that it goes up with and is equivalent to the velocity that it will come back at the same level, at the level of the building. So we're just going to change the sign and say negative 15 meters per second, and then it is going to give us the same answers if we just take this and substitute this. So all what matters is that you define your variables according to the section of motion that you have been given. Now let me just wrap this, and then we'll continue with the second question. So when it continues, it says that now the ball strikes the ground at 3.36 seconds after it is thrown upwards. So we are told that what does our Q represent? Our Q represent the time it takes for the whole motion. So if we check the motion of the ball from the height of the building here, the ball goes up. Is it a ball or a stone? Yeah, it's a ball. I know sometimes they use stones also. So, and then it hits the ground. After it hits the ground, it goes up. And then after it goes up, so they are saying that from here to here, they say that until it strikes the ground, it's gonna take 3.36 seconds. So that's what we are told, that all this is gonna take 3.36 seconds. And then they say that calculate the value of Q. So the value of Q is the velocity that is gonna hit the ground with. So you must note that the section of motion that we are using here is the section we can either choose to use the section from projection to this section here, or we use the section from, no, this is not the section. We can use the section from maximum height to the section which it hits the ground. Because what are we looking for? The final velocity here, the velocity that it comes back with and hits the ground. So we can use this section, or we can use the section for the whole motion, or we can use this section. So we can either use that. So let's use the one for the whole motion. So if we consider the section of the whole motion, so now we are going to define our variables from the time of projection to the time in which it hits the ground. So now if we start with our initial velocity here, so our initial velocity is going to be the velocity of projection. Note that all our calculation is up as positive. So at the time of projection, the velocity that it went up with is plus 15 meters per second. And then the final velocity is the velocity in which it hits the ground with here. So the velocity that it hits the ground with, we are looking for it. And another thing that we can know about it is because we said up is positive. So because it will hit the ground going down, so this velocity, it has to be negative. We have to calculate it and find a negative value. And then another thing that's always there is gravitational, so it's always downwards. So if up is positive, this one is also gonna be negative. And then another thing that we also have to note that the question has given us is that the whole motion takes 3.36 seconds. So we can just come and say change in time here, and change in time is 3.36 seconds. And then we just find a formula in which you can plug all this. It's the very same formula that we used in the previous one. V final equals to V initial plus a change in time. And then now we're just gonna plug in everything and solve for our question. So now here in V final we are solving for it, and then V initial, we are plugging in plus 15, and then you can say negative 9.8 meters per second, and then the time here is 3.36. And then you just solve, just press it. This one is on a straight line. Come and say 15 minus 9.8 times 3.36. So the answer here we got negative 17.928. As I said, this one is going to be negative. As you can see that it's negative. What does negative tells us the direction, to say that it is 17.93 meters per second way downwards. So we got this one's, the value of Q is 17.93 meters per second. So that's the value there. So now let's go to the following question, which says that the ball bounces to a maximum height of 3 meters after it struck the ground. So we are told, okay, let me just wrap this so that I illustrate this with the diagram, so that we can go to the following question. So it then continues to say that the ball bounces to a height of 3 meters after it strikes the ground. So if we check the scenario here, it says that is the collision with the ground elastic or inelastic? Without the answer, explain the answer without the use of calculations. So we have to first see the scenario and evaluate from there. So they are saying that first it fell from a 5-meter high building, and then after it's going to spend some time at the ground, and then it bounces, and after bounces says that it reaches a height of 3 meter. Now it reaches a height of 3 meter, and they say that is the bounce inelastic or elastic. So first you have to know your terms, to say that what does it mean for a bounce to be elastic. For a bounce to be elastic, the total kinetic energy of that item has to be conserved. If but because here there's no momentum, but in general is to say momentum, the sum of momentum is conserved, and also the kinetic energy is conserved. But here we are just dealing with kinetic energy only, because here we are dealing with the velocity, on how the velocity is going to change. So if this bounce, if some energy were not lost, because we know that if this ball hits the ground, also in reality some kinetic energy is going to be transferred to sound, because if the ball hits the ground, you hear that sound of the ball hitting the ground. And also there's also gonna be friction there when the ball hits the ground. There's also gonna be there's friction, there's sound, there's also heat. So those are possible ways in which kinetic energy can be lost. So if its energy was energy was not converted, it would have hit the ground and come back at the same height. But what is telling us that kinetic energy is lost is that it came back 2 meters less from the initial. So that's how we can conclude. But if kinetic energy is not lost, it will have continued to the same height, just like how um, Newton's first law puts is to say that an object will continue with its constant velocity unless a force acts upon it. So here we are seeing that some energy is lost, so it cannot continue and come back to the same height. So, but if it was in a vacuum, it will just continue to do 5 meters, 5 meters, 5 meters, and continues like that unless another force acts upon it. So now we can see that because it didn't continue back to the same height, there is some energy that was lost. So the way that we can explain this without using calculation, you can say that the one thing that makes us to deduce faster is that the ball did not come back at the same height. We see that the height here of 3 meter is actually less than the one of 5 meter. So it came back at a lower height. So that's the first answer. And then now you have to substantiate to say that kinetic energy is lost. Kinetic energy is lost or converted to any of these. That's how we are going to find the answer to say that it is inelastic, to mean that some energy is lost, kinetic energy is not conserved. And why is it inelastic? The ball did not come back to the same height, it lost 2 meters. And then another thing is that kinetic energy is converted to any of these. So that's how we are going to answer that question, which appears to be a very tricky one. And the last question, it involves graphs. So it says that sketch a velocity versus time graph for the motion of the ball from the time it was projected uh, until it reached the maximum height after it bounced. Show the numerical values of the graph. So here they want us to sketch. So what you have to know is first you have to choose direction in the graph. So because here they didn't say we must use up or down as negative, we'll just use the one that we have been using for the whole of these calculations. So there are things they want us to indicate. So the first thing that you have to note is that here you are going to put the dependent variable, which is the velocity here, which is in meters per second. And note that this is the negative side, this is the positive side of the velocity. Is because velocity here, it can be negative when the ball is going down, because we said up is positive. So whenever the ball is going down, our graph has to be on the lower half of the graph. So, and then the time, which is the independent here, so whenever the ball is going up, it has to be on the top. So what we have to note, let me just throw the motion of the ball again so that we can take from the motion on how the ball is moving. Let me just put it here. So we see that it was projected downwards, it bounced, it came back. So now the ball starts by going up until the maximum height. And you must note that the maximum height, the velocity is zero. The velocity is zero. So you note that this is the 0 point. So it starts when it's positive and it goes to a point where the velocity is zero. So here's the point where the velocity is going to be zero. It's going to start going up, and then it goes to where the velocity is 0. And then what happens now? It goes down. When it starts going down, because up is positive, down is what is negative. So from here to here, it's gonna go down. So here it's gonna go down, and then down is negative. That's why the graph is on the lower half now, and then it's gonna be equivalent to this as up until the ball reaches this point. So this half has to be equal to this, but they don't really check that. But you have to be precise with your throwing. And then from this point, because now it's going further from the point in which it was projected upwards, this one will be longer. This one will be longer. As you can see that this section here is represented by this section, and also this section here is represented by this section. That's why you can see the proportional in the height. So this is where it gets a little complicated now at the bounds. So you have to know how to also represent the bounds. And a thing that makes a bounce pretty a little complicated is that now after it bounces, it's going to change direction. After now, when the ball bounces, let me just remove these lines from my diagram so that I can represent the bounce well. So if we check the bounce here, now after it bounces, so we see that it's negative. Our graph is negative now because we ended here. We ended before this bounce. So now we have to represent the second bounce. After it bounces, it's going to be positive. So it has to start from here now, because what? Because it's now positive. But you must note the time to say that the time is starting at this level where that one ended. So so it's also gonna be contact time. So you have to leave contact time in between, and then now the ball is gonna start with a velocity which is less than the velocity that it hit the ground with, and then you just come and say, now is this is the ball going to its maximum height where the velocity is 0. So here it reaches its maximum height, and after it reaches its maximum height, we're not told now but the ball is going to come back down again. When it comes back, that's when it's going to be more negative going there. So that's how we represent it. They say represent the initial velocity. So the initial velocity is this one. So I'm representing it to say that it's 15 meters per second. And then represent the time p. Time p is a what? It's our maximum height. So this is the time p. And then represent the velocity q. Velocity q is what? The velocity in which it strikes the ground with, which is this one. So that's how we represent it. So that now is at the end of our session. So thank you for watching.